You know, from a car just cruising down the street to a ball dropping from your hand, we see things moving literally every single day. But have you ever really stopped to think about what moving actually means? I mean, it seems so simple, but the physics behind it, wow, it's actually incredibly cool. So let's get into it and break down the science of motion in a straight line.
So here's our game plan. We're going to build this whole thing up step by step. We'll kick things off with what it even means for something to be moving. Then we'll figure out how to measure that movement, how far it went, and then how fast it's going. And finally, we'll see what happens when things speed up or slow down, pulling it all together to understand the basic types of motion you see all around you.
All right, so let's just start with a really simple question. Are you moving right now? I mean, you might be sitting perfectly still in a chair thinking, no. But the answer is, well, it's a little more complicated than you might think. And that complication is the key to everything else we're about to talk about.
To even begin to answer that question, we have to start with the most fundamental idea in all of motion, that everything, and I mean everything, is relative. To say something is moving, you first have to decide what it's moving in relation to.
This is a great way to picture it. It all comes down to what's called a reference point, or as you see here, a titik acuan. Just look at Sadiq walking from his house to the market. Now, if we use his house as our reference point, he's moving away from it. Simple enough. But if we choose the market as our reference point, he's moving towards it. It's the exact same walk, but how we describe it changes completely, all based on our point of view.
So this is the big takeaway, the formal definition. Motion isn't just a change in position, it's a change in position relative to something else. Without that reference point, the word motion is kind of meaningless. So back to our question, are you moving? Well, relative to your chair, probably not. But relative to the sun, oh yeah, you're hurtling through space at about 67,000 miles an hour.
Okay, so we've got it. An object is moving. The next obvious question is, right? How far did it go? And in physics, there are two very different ways to answer that, and the difference between them is absolutely critical. Okay, picture this with me. Let's say you start out, you walk 4 kilometers west. Then you just turn right around and walk 3 kilometers back to the east. It's a simple little trip, but it's the perfect way to show the big difference we're about to see.
And here they are. On one hand, you have distance. That's just the total ground you covered, the whole step-by-step journey. That's the 4 kilometers plus the 3 kilometers, so 7 kilometers total. It's just a number. But displacement? Oh, that only cares about two things: where you started and where you ended. The straight line from your front door to where you stopped is just 1 kilometer to the west. See the difference? It has a size and a direction.
And this is the classic example that really makes it click. A runner does one full lap around a track. They've definitely covered a distance, right? Let's say it's 400 meters. But because they ended up exactly where they started, their displacement, their change in position from start to finish, is a big fat zero. From a physics point of view, they went nowhere at all.
Now, this whole distinction between distance and displacement is so important because it leads us directly to our next pair of ideas: speed and velocity. They sound almost the same, and we use them interchangeably all the time, but just like before, one is a simple number, and the other one has direction packed in.
And here's the breakdown. Speed is exactly what your car's speedometer tells you. It's how much distance you cover over a certain amount of time. That's it. But velocity, that's your displacement divided by time. It tells us not just how fast your position is changing, but also which way it's changing. So you can have a speed of 60 miles per hour, but your velocity would be 60 miles per hour north.
Think about it. In the real world, things almost never move at a constant, steady velocity. We speed up, we slow down, we change direction. And this change in velocity, well, that's what physicists call acceleration.
Now here's the key thing to get about acceleration. It is not just about speeding up. Anytime an object's velocity changes, and that could be its speed, its direction, or both, it is accelerating. Hitting the gas pedal? That's acceleration. Hitting the brake pedal? Yep, that's acceleration too. Even taking a turn at a perfectly constant speed is a form of acceleration because your direction is changing.
Now, when we're just talking about a straight line, it gets a lot simpler. Positive acceleration just means you're speeding up, and negative acceleration, which you probably call deceleration, means you're slowing down. It's really just the gas pedal versus the brake pedal. They're both causing acceleration. Okay, so we've got position, displacement, velocity, and acceleration. We have all the puzzle pieces. Now we can put them together to define two really important types of linear motion that describe tons of stuff we see every day.
First up, we've got uniform linear motion. Honestly, just think of this as the most simple, predictable motion possible. It's an object moving in a perfectly straight line at a perfectly constant velocity. Its speed never changes, its direction never changes, which means its acceleration is zero. Imagine a train on a long straight track with the cruise control locked in. That is perfect uniform linear motion.
And then you have its more interesting cousin, uniformly accelerated linear motion. This describes something moving in a straight line where its velocity changes, but it changes at a super steady, predictable rate. So its acceleration isn't zero, but the acceleration itself is constant. The absolute perfect example is just dropping something. Gravity pulls on it, making it speed up at a constant rate.
So let's lock this in, nice and simple. Uniform linear motion, or GLB. The velocity is locked in, which means zero acceleration. Uniformly accelerated linear motion, or GLBB. The velocity is always changing, but the rate of that change, the acceleration, is locked in. These two ideas are the foundation for so much in physics.
All right, let's see what this actually looks like in practice. Now, graphs can sometimes look a little intimidating, but this one is really just telling us a simple story about a car ride. The line going up shows the car's velocity, and the line going across shows time passing. Let's trace the story.
This just illustrates both concepts perfectly. Look at the first 5 seconds. See that flat horizontal line? That means the velocity isn't changing. It's constant at 30 meters per second. That's our uniform linear motion, our GLB. Then, right at the 5-second mark, you see it. The line starts to slope down. The driver hit the brakes. The velocity drops in a perfect straight line, which means it's changing at a constant rate. That's our uniformly accelerated motion, specifically uniform deceleration.
In the end, it all comes back to this one single powerful idea. Everything we've talked about, distance, velocity, acceleration, it all depends on having a starting point, a frame of reference. Motion is never absolute. It's always a story, and it's always told from a particular point of view. So, we've built a really solid foundation for understanding how things move in a straight line. But the world isn't all straight lines, is it? What happens when you throw a ball or a planet orbits the sun? That's where things get really interesting. That curve opens up a whole new world of physics. What kind of forces make that happen? Well, that's a question for another time.